So we're going to talk about verifying using Python, a framework I've written called Cocotb. Hopefully we won't have any technical problems because I'm using someone else's laptop, so I don't know about you guys, but using someone else's computer is much harder than using mine. So Cocotb is an open source Python verification framework. We set up with a few goals when we designed Cocotb. So based on our experience of using commercial verification frameworks, well, the industry standard verification frameworks in a commercial setting, such as UVM, we were convinced that there was a need to reduce the overhead of creating test benches. So in the commercial world and in a lot of academic projects, verification is the limiting factor. So we wanted to try and redress that balance, not simply by creating a tool that would generate boilerplate UVM test benches, but to try and root cause fix the problem. So we wanted to bring hardware and software engineers together and to allow the software team to contribute to the RTL verification. We wanted the RTL team to kind of more closely interact with the software team and to try and integrate their software and hardware together earlier on in the process. And we wanted to be able to support existing projects. So being compatible with VHDL and system Verilog was kind of a key driver. And finally, we wanted to use a high-level language to sort of improve the accessibility of verification to newcomers or to software engineers or to people without a traditional hardware background. So before we start, there's a kind of an assumption that we started out with, which is surprisingly controversial, that verification is entirely a software task. Hardware people don't seem to like that idea, but it's unfortunately true. If we look at your typical verification flow, you have some simulator. I should stress that this is functional verification in simulation. So you have your design under test, which is running inside a simulator. The simulator might provide some kind of waveform, assertions, debug capability. But then you use something to stimulate the inputs of your design, to sort of check the outputs of your design, validate that the behavior is what you expect, and that's entirely software. So that's obvious, but surprisingly radical for some reason. So we decided to use a software language to do our verification. Yes, exactly. And we chose Python, kind of for the reason we stated earlier, that it's accessible to hardware engineers and software engineers. It's an area where different teams can come together, and it's very accessible to all kinds of engineers from different backgrounds. It allows you to plug stuff together very quickly. You can call out to other languages. It's the kind of ultimate glue language. And it permits a very rapid development, which is really our goal here, is to try and speed up the verification process, which is generally limited by engineering effort. Okay, so Cocotb itself, we start on the right. You've got your design, which is running in your simulator, so you still depend on some kind of external simulator. Your design might be VHDL, system Verilog, or some kind of mixture of the two. We then use the C language interfaces provided by the simulator to access the design. We've put a layer in between, which we call kind of generic procedural interface, which abstracts the differences between VPI, VHPI, or FLI. And then we expose that to Python. And on the Python side, you have we use coroutines for concurrency, so you can have massively parallel, many flows of execution running in Python. So your test is made up of lots of coroutines running in Python that are accessing the design through this C++ kind of layer in the middle. Okay, so if we take a look at an example, this is something that might be considered slightly difficult to do if you were just limiting yourself to VHDL system Verilog. And this is the kind of area where being in Python really shines. So we have, let's say we've got some design which is responding to Ethernet packets, so it's like an ICMP stack that's going to respond to pings. And we want to use the Linux command line ping utility to ping our design running simulation. So to do that, we need to create a virtual interface in Linux, and that's going to give us a file description we can use in our simulation. We hook up our drivers and our monitors to the design, and then we kind of receive packets from our file descriptor, send them into the design. We sort of deserialize the output of the pins back into transactions and send them back up to Linux. Okay, so this is conceptually quite simple, but it's the kind of thing that people don't tend to do just because it's awkward. So using Cocotb and Python, it's very, very simple. So if we just walk through this example code, we have a test. Every test is just a function that takes a handle for design as the first argument. We then hook up our drivers and our monitors to the design. And again, this is where Python really stands out because we have reflection and introspection capabilities in Python. Kind of hooking stuff together is really easy. We can sort of discover all the signals with this name, or we can query the design dynamically. So we're just going to look for all the signals that match this name associated with this clock, and that's our driver, same with the monitor. Then we're going to create our virtual interface. You could say that this is sort of cheating slightly because I'm just hitting a load of code in function here. But again, one of the advantages of Python is if you type into Google Linux untap virtual interface, the first hit, you get 20 lines of code, you put in a function, you're done. Right, so the accessibility and tapping into the ecosystem that's available to software engineers is a major driver. Okay, we get the file descriptor for our TUN interface, we wait for a packet to arrive, we send the packet into the design. We're using the yield keyword here because it's a coroutine based environment, so we yield, control back the simulator to allow time to advance. We're going to wait for an output, and then we're going to send that back over our file descriptor to through our virtual interface. So I'm going to try something very daring here and actually run a demo on someone else's computer. Let's see if this works. Yeah, okay. We're going to have to default on that. Right. So probably nobody can see that, I'm guessing. Okay. So this isn't that. Let's see if I can type. We have to run under root because I haven't set up the permission properly, and I have to type in my password correctly. Okay. So this is now this is running Icarus, and we've created a virtual interface in our simulation. Apologies for the size of that. But if we switch back to the next terminal, we can just ping our simulation, and we can see that we get responses from our sim. That's going back to ping. So in 10 minutes and 50 lines of code, we've created an environment where we can run unmodified Linux command line utilities, co-simulate them with our RTL running soon. Okay, so that kind of really explains what we're trying to do, and hopefully that's a kind of nice, simple example of how clean your test bench code can become if you advantage the high-level language. Right, let's think about. So I'm probably the only guy here, from what I can tell, who's not designing their own CPU. So we create accelerators and we write software to run on those that communicate with that custom hardware. So we run a lot of software, we do a lot of RTL design, but we're not designing our own processor. And one of the problems we have is how do you co-simulate the software you're writing against with your RTL simulation so that we can integrate at the simulation stage. And in the FPGA world, a lot of your device access is kind of done, memory mapped. Some people even use DevMem, but you might be using a UIO drive or something, and you mmap your device, and then you just kind of you've got a memory mapped area you can just access your device directly. Okay, this is kind of quite awkward for co-simulation because obviously it's hard to execute this software in user space without having some kind of package. So what we do here is we can run that software on the ptrace, we can trap on the open and the mmap, we create a fake file backing this device, we f-truncate it to the right size, and then we can inject an mprotect call into the tracey process so that we get a segfault every time a memory access occurs, which we then trap, and then we can do some funky stuff to determine whether it was read or write access, the kind of width of that access, and then we can call down the simulator to perform whether it was a read or write, and update the memory mapped area. So this allows us to kind of run unmodified user space software that works in this way to interface to your device, and we can sort of co-simulate that quite easily. It gets a bit more fun if you're developing kernel drivers. So obviously people don't like it when they're developing a kernel driver against buggy hardware and their box panics all the time. So you like to develop your driver in QEMU or some other emulator. So we've kind of created a device for QEMU, which is not open source yet, but we're hoping to open source soon. Sorry, Rob. And yeah, so this is primarily for kind of doing PCIe devices. So as QEMU boots, it communicates with the simulator to get the base address mappings for all the bars. We then create a device in QEMU. Any DMA from the simulator gets sent over the socket, and we update the QEMU view of the memory map. And similarly, any accesses from the driver we trap and we send over the socket. So we've got a kind of transactional level model abstraction here between QEMU and our simulator. So we can develop kernel drivers in QEMU against our RTL running sim. Okay, simulator support. So we support kind of all the major commercial simulators and some of the open source ones. Anything that's in theory compliant with VPI or VHDL should work with Cocotb. FLI, Mentor don't kind of like us for some reason, so we've struggled to get a license to develop FLI. It did work at one point, but it's kind of a bit rotted, I'm afraid. So if anyone wants to donate us a Mentor license, or they're using FLI, then get in touch. Right, so there's a whole load of stuff that we won't go into because we're running behind. But you can do things such as dynamically discover all the objects in the design, automatically attach protocol checkers to all buses that match a certain naming convention or type. You could kind of automatically insert cross-block domain checks and things like that. So the discovery aspect and the dynamic introspection that you have available in Python is very powerful. Your design can be VHDL or system Verilog. You have mixed layers of hierarchy, and the interface from Python is always the same, so you can kind of traverse through the language barriers without kind of knowledge of what language the design is in. We have automatic test discovery, so just the very act of writing a test adds it to your regression. We output test results in JUnit format, so we can plug into tools like Jenkins. And again, this is all kind of trying to make it very quick to develop a regression for a given component. So just the very act of writing a test is enough to have that test automatically run, the results being reported, etc. We have some things to generate all the different permutations of kind of tests based on some parameters. So you can very rapidly multiply up effort just by effectively permutating through different configurations. We've got some BFMs built in, so we try and follow the Python batteries included model. And that's kind of gradually growing. And we've got there are some projects, including a CERN project for Atlas, where the code is on GitHub and Travis CI is running Cocotb automatically. So it's possible to have a sort of completely hosted open source flow that's run automatically. What we're working on next, we've got a few sort of things on the horizon. So we want to do a bit more work on the kind of this online stuff, which Julius hinted at earlier. So we're looking at not just Cocotb, but generally the idea of sort of automatically hosted regressions that plug into GitHub. If you're interested in constrained random, there's a whole, as Clifford was mentioning, there's kind of all sorts of interesting open source stuff out there that you could, most of them have Python binding, so that would be an interesting area. And as Rob mentioned, we were talking about American Fuzzy Lock earlier. That's something that we've been looking at for a while, which would be really nice to find some way of automatically instrumenting your design. So without having to write sort of functional color points, you can do genetic exploration of stimulus and intelligently feed back your coverage information to your genetic algorithm to try and hit coverage points. We've got some kind of prototypes of how to do functional coverage using Python, and we would like to sort of plug in finally a utilise standard. I think it took about 7 years to write an XML schema. It's called joys of EDA standards, but there's we do kind of have to accept that we need to plug into the existing infrastructure. So there are a lot of projects, there are a lot of tools, there are standards, so we're trying to sort of use those standards where we can. It's an open source project. We're a small, I would say startup, but we've been going for a year, so that probably doesn't qualify us. But we offer commercial support. We do feature development, so sponsored features if people particularly want something in there. We're starting to run training courses, and we kind of do consultancy. If anyone's interested in using Cocotb or adopting it as part of their flow, we can help out with that. If you want to get involved, try it out. Obviously, it's on Git. It should be quite easy to find. Report any bugs, raise feature requests, comment on issues. All the usual GitHub fun. Submit pull requests. So we tend to accept stuff. We're probably possibly a bit too accepting. At the moment, we just take we've got quite a lot of contributors now. So yeah. So and if you're interested, if there's something that you would like to see in there, then you can sponsor a particular feature. Because at the moment we don't have much time, so we need to try and fund our development in some way, unfortunately. And you can tweet us, PBCocotb. Thank you.
You mentioned a growing library of bus functional models.
Mm-hmm.
Are those, I guess, which bonus there, for instance? I haven't looked at it, so I just want to ask about that really. Which ones?
At the moment, the growing library is mostly Avalon. So we've got, internally, we've got a PCIe sort of TLP level model that we're tidying up. So that should come along soon. Wishbone, I guess it would be trivial to do. It's a very simple protocol. So it's not there yet, but it could be added very quickly if someone had a need for it.
What's wrong with mine? Which won't be about?
Right, I think it's a pretty cool thing. Did you also think about doing hardware in loop testing, so that you do both the simulation and the hardware testing with the same software framework?
Yeah, that's something we've explored a little bit, particularly with the kind of SoC. So we've got the Zinc and Cyclone 5 dev kits with the arms on, so we're looking at kind of the right point to hook into this so that you can push your transactions through a real design. We spent a few weeks playing around. The problem is at the moment the performance penalty of running Python on an ARM device is kind of it's all a bit of a pain. I think it would be nice. What you really want is sort of synthesizable transactors and keep everything at the transaction level. And then there's scope there, but it needs clearly defining and it needs a lot more time to play around with it. And our problem at the moment is we've got loads of ideas and not enough time. I think that's probably a common fate.
Functional coverage. Can you say a few words about the status of that? Is that something that you're building into Cocotb, or is that another module you plug in or something?
So that's something we're building into Cocotb. So the idea is that you can, functional coverage is effectively defining a set of counters that increment based on certain conditions, and complex coverage, you might have some kind of small multiple cycle state tracking device to decide whether which bin to increment or whatever. So it can be quite convenient to do that in Python. particularly also transaction level coverage. So for example, if we do a lot of networking stuff, so shoving packets around, and actually we already have the internal representation of that packet, so we can do a lot of functional coverage just in the Python level without having to query the design. So we can say, right, simple example, packet lengths. So we can track all the packet lengths we're sending in, and what we're looking at is how to do that really nicely in Python. So we've got a kind of example where you would just use a decorator on the driver or the monitor, which then you get a hook, and you can define some very easy. Out of the box, you get things like packet length, the gap between packets, errors, and things like that. But we've got some kind of proof of concept code that's sat in the branch at the moment. Bit neglected, but
I think that would be quite interesting if you were going back to the discussion we had before about getting metrics on blocks.
Yeah.
That would be,
So the driver there is, the open source simulators unfortunately do lag what you can achieve with a commercial offering. So I don't think there's any open source simulator that supports all of System Verilog. There are very few that even do some of the simple System Verilog constructs, and things like assertion and functional coverage are kind of quite far behind. So if you could, if we can provide that capability from Python, then just using something like Icarus, you can have quite an advanced, you can have constrained random functional coverage, you can have genetic stimulus generation. So you kind of got quite powerful, you don't need to use the tools, you don't have to rely on the vendors. So that, it's a driver for that, but time.
Does it make sense to have support for chisel in this going forward, and what would that take?
We did have a feature request a couple of weeks ago, I think, from one of the chisel guys. So the interface, if we skip back a bit, what we've done here is effectively we've defined a set of functions that have to be provided by whatever effectively simulator or backend is running it. So you've got things like set a value, get a value. Where it gets a bit more complex is the kind of dynamic discovery of names. So you can traverse the hierarchy and say what objects are below this parent. So you could, in theory, this could be your C++ or System C backend from Chisel, and you could hook into it here. So that's a possibility, but whether, I guess one of the advantages of the C++ generation is that you can execute very fast. Obviously, here we're aiming for development speed rather than execution speed necessarily. So it is Python. It will work with PyPy, but you're probably not going to be able to boot Linux if you're sort of running some kind of cycle by cycle driver stuff from Python. It's going to take you a long time to boot Linux.
And just in a VMM or UVM environment, the scoreboarding is kind of essential. I didn't really get how do you do the scoreboarding here?
How do you define scoreboarding? So, right, you need, effectively, if you're using UVM, you have constraints that kind of provide a mechanism for generating randomized input that conforms to certain conditions. You have some kind of model of the system, which you use to effectively equivalence check the simulation versus your expected behavior, and then you have functional cover points which define certain areas of the design that you want to exercise. So your scoreboard is effectively comparing your design against your model. So this is again one of the nice things about Python is often you might have a reference model in software, and it's very easy to use that reference model from Python. So one of the examples that I've got on GitHub is, for example, a JPEG encoder from OpenCores, where we're sending images through, and then we're using the Python image library to compare the original bitmap versus the JPEG for similarity, and they have to match within a certain percentage. So the idea of scoreboarding is just comparing the expected output versus the output of the design versus what you expected. You need some kind of reference model, And I would argue that writing a reference model in Python or using an existing model from C or C++ or whatever is much easier than trying to write some TLM model in system Verilog just for the purposes of verification.
But a slide showing your solution for that would maybe be nice.
Yeah, I'll put that in the next presentation. Probably best to look at the code examples. I can point you at some examples.
Cool. All right. Well, thank you very much for that, Chris.